Today, I'd like to talk about momentum. Momentum's a vector, and you'll fondly recall the song M times V, just a little momentum. So momentum is M times V, and it's so fundamental of a thing that Newton referred to it not as momentum, but as the quantity of motion. So he said how much something is moving is emphasized by its mass times its velocity. So obviously if something is not moving, then its momentum is 0. That's reasonable. And if something is moving fast, then its speed will be big, so its momentum will be large. Also, something else that could have large momentum would be something with big mass and reasonable velocity. But a big mass would also represent that more movement is happening. So I hope that Newton's idea is reasonable to you also. But as we go on, this definition of momentum is fine, but I'm interested in the change in momentum. And this is a quantity that we can call impulse. And the book that we're using right now says that impulse is a capital I, and it is simply the change in momentum. So this statement is the impulse momentum theorem. It's pretty cool, but let's write this out. If we assume this delta says change, and momentum represents two things, so we're talking about the change of m times v. Both of these things could change in principle, right? So we're going to have to be careful. Which one do you think is going to be changing? Probably the velocity. We will consider, in the next video, we'll consider what happens if the mass of a thing changes, because that's very interesting also. But let's assume that the only thing that's changing is the velocity. So then we can take the m out of the delta. Delta is kind of like a derivative in a sense. We can pull the m out because we're assuming that it's constant here. So this is m times delta v, change in velocity. Okay, now what I'm about to do is I'm about to multiply it by 1. Would you agree that I could take the impulse and multiply it by 1? Sure I could, right? So I'll multiply it by 1 and I'll write 1 like this. Delta t over delta t. You know where I'm going with this? This is about to be awesome. I've got m times delta v times delta t over delta t. What can I do?
The delta t's are 1.
The delta t's are 1.
It just becomes m times v.
M times v. Oh, you're going backwards though. I want to go forwards. I put this in here.
I wasn't paying attention to the beginning.
No, of course you weren't. What, Jordan?
You can put a v over t.
Yeah. I can write this as m times delta t times delta v over delta t. And you know what delta v over delta t is, right?
Change the acceleration.
It is. It is the acceleration. It's not the change in the acceleration, but this is actually the definition of the acceleration vector. So I've got m times delta t times the acceleration vector. And if we keep going, let's keep going. You see it?
Yeah.
This is mass times acceleration times delta t. Have you ever seen mass times acceleration before?
No.
Yes.
You have seen those two multiplied before, haven't you? Yeah. What is mass times acceleration?
Force. I believe it's force.
What kind of force?
Net.
Force. So this is the net force
Don't want to be wrong on that.
times time. Interesting. This says add up all the forces over time, and that is what impulse is. It's also change in momentum. And this is what Newton wrote as his second law. We write net force is mass times acceleration, but Newton wrote change in momentum is net force times time. This is not calculus-based yet. You want to make it calculus-based?
Of course.
Let's do it. Let's do it. Here's what I want to say. We could do one thing. What I want to do, there are two ways we could look at this calculus-based. One thing I want to do is just say that delta p, the change in momentum, I don't want to say that it's just the average force, average net force times the time. I want to say let's integrate the force over time. So that means I add up all the force as time happens, and I can find the change in momentum. So if you have a graph of force as a function of time, and the force gets bigger, 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 bigger as time goes on, then you find the area under here, and you could tell me how much the momentum has changed. And we did that a little bit in the calculus lessons that we've already seen. So this is the definition of change in momentum. Another cool thing that we can do is I still don't like this delta over here. we could take this equation, yeah, let's take this equation and write it like this. Delta P over delta T is equal to net force. Another way that I can write net force is the derivative of momentum as time goes on. This is a derivative. It's not deltas anymore. It's the derivative of momentum as time goes on. And that's what net force is. Of course, momentum is a vector also. Being sloppy with my vector hats. Okay? All right, fair enough. What else should I say about change in momentum? I want to point out that this impulse thing is the integral of force over time. But you've seen another integral that's very similar to this. I'm going to give a challenge to my people in the back of the class. Hey, back of the class people, check this out. If I have the integral of force over distance rather than the integral of force over time, what's that?
Work.
It's work. So notice how similar impulse, change in momentum, and work are. This is an integral over time. That's an integral over distance. Very, very interesting. And work and change in momentum are pretty darn related. Pretty darn related. Let's see what else we should do. The next thing I want to talk about is net force. This idea of net force has already been in here, so we need to address it a little bit more carefully. If we are interested in finding net force, we could say that net force is equal to the sum of all internal forces plus the sum of all external forces. Reasonable, right? The net force on a thing is a sum of all the forces that act on it. So all the internal forces plus all the external forces. But one of the cool things is Newton's third law. Newton's third law says that force of thing 1 on 2 is the opposite of force of thing 2 on 1. That means that if I am both thing 1 and thing 2, i.e. a force acts on me, if I'm pushing my head backwards, then my head is pushing my hand forwards. And every internal force is canceled by an equal and opposite internal force. This statement requires that the sum of all internal forces is 0. So we can go just a tiny bit further with this and say that the net force on an object is the sum of all the external forces that act on that object, because every internal force cancels out. Pause. Starting from the statement of Newton's third law, that every force has an equal and opposite paired force to it. And one force acts on thing 2, and the other force acts on thing 1. I want you to consider a system of 2 objects that run into each other and have, therefore, some forces on each other. So let's consider this equation for those 2 objects. I can multiply both sides of the equation by anything I want, right? I can take the white chalk and I can multiply it even by a variable. We know from a moment ago that force times change in time is impulse, which is the same thing as change in momentum. This is a change in momentum, and that's equal to the opposite of a change in momentum. This is weird. It seems to imply something very depressing about change in momentum. Let's be a little bit more careful, though. This is a change in momentum on the thing that feels this force. So it's the change in momentum of thing 2, and this is a change in momentum of the thing that feels the opposite force, and this is the change in momentum, therefore, of thing 1. So what this says is when 2 things run into each other, whenever any 2 things in the universe interact, and believe me, there's a lot of that going on, when things interact, they change momentum in a very similar way. I guess this means that if this one gains 3 kilograms per second, and then this one would lose 3 kilograms per second. So it's like they're transferring momentum from one thing to the other thing. Let's take this and look at it a little bit further. Take this equation upper. We got change in momentum of thing 2. So that's P2 final minus P2 initial, and that's equal to negative P1 final minus P1 initial. Do I have everything right? I got vectors, hats on everything. Final minus initial, 1, 2, everything's cool. Okay, let's distribute the minus sign. I'll have negative P1 final plus P1 initial. And I want to get all the initials on one side and all the finals on the other side. Let's put the initials on the left side. I'm going to get on the left side, I will have, on the left side I'll have I'm going to have negative, I'm going to put everything on the right side. On the right side I have P1 initial plus P2 initial. Sorry that it's a little bit backwards, but I don't want it all to be negative. That would be annoying. And then over here I'm going to have P2 final plus, look at this, I'm going to move this to the other side so it becomes positive. I get P1 final. This says that this is actually P total initial, and this is P total final. This says that the total momentum of the system of two things never changes. Whenever two things interact, the total momentum of the system is conserved. So this leads us to our second conservation law, very, very similar to mi is mf. We can then write pi is pf, and there's an implied total or system on that equation also. So we can use this to solve lots and lots of problems. Sam, let me give you a quick example. I might, eraser, I might think about two things, and I might have to write a very tedious equation. The mass of thing 1 times the velocity of thing 1 initial plus the mass of thing 2 times the velocity of thing 2 initial is equal to, these are vectors, the mass of thing 1 times the velocity of thing 1 final plus the mass of thing 2 times the velocity of thing 2 final. Tedious, right? Oh, this is the general statement of the conservation of momentum. You have to write it out. Sometimes things are a 0. An example of that might be only one thing is moving initially. Then you could say thing 1's moving, but thing 2 is not moving. That would be a cool example. Another example of where things might simplify is if we say the two things move together. It's a special kind of collision we'll address in just a moment. But if the two things move together, then the final velocity of thing 1 is the final velocity of thing 2, and we can make a little bit of algebraic simplification to make this problem easier. But if you start with this equation, you can solve any conservation of momentum problem. Please use this equation wisely. Memorize the heck out of it. Let's go into some examples in just a moment. By 1. Would you agree that I could take the impulse and multiply it by 1? Sure I could, right? So I'll multiply it by 1 and I'll write 1 like this. Delta t over delta t. You know where I'm going with this? This is about to be awesome. I've got m times delta v times delta t over delta t. What can I do?
The delta t's are 1.
And the book that we're using right now says that impulse is a capital I, and it is simply the change in momentum. So this statement is the impulse momentum theorem. It's pretty cool, but let's write this out. If we assume this delta says change, and momentum represents two things, so we're talking about the change of m times v. Both of these things could change in principle, right? So we're going to have to be careful. Which one do you think is going to be changing? If something is not moving, then its momentum is 0. That's reasonable. And if something is moving fast, then its speed will be big, so its momentum will be large. Also, something else that could have large momentum would be something with big mass and reasonable velocity. But big mass would also represent that more movement is happening. So I hope that Newton's idea is reasonable to you also. But as we go on, this definition of momentum is fine, but I'm interested in the change in momentum. And this is a quantity that we can call impulse, probably the velocity. We will consider, in the next video, we'll consider what happens if the mass of a thing changes. because that's very interesting also. But let's assume that the only thing that's changing is the velocity. So then we can take the m out of the delta. Delta is kind of like a derivative in a sense. We can pull the m out because we're assuming that it's constant here. So this is m times delta v, change in velocity. Okay, now what I'm about to do is I'm about to multiply it. Today, I'd like to talk about momentum. Momentum's a vector. And you'll fondly recall the song M times V, just a little momentum. So momentum is M times V, and it's so fundamental of a thing that Newton referred to it not as momentum, but as the quantity of motion. So he said how much something is moving is emphasized by its mass times its velocity. So obviously